Welcome to aminacademy.com. In electrical engineering, let us discuss about charging and discharging of a capacitors. What is charging a capacitor? The capacitor is fully charged when the voltage of the power supply is equal to the array equal to that at the capacitor terminal. That means the power supply voltage is equal to the capacitor voltage, then it's called fully charged. This is called capacitor charging, and the charging phase is over when current stops flowing through the electrical circuit. When the power supply is removed from the capacitor, then discharging phase begins. Here, look at this figure. Here, the voltage terminal is connected through switch and resistance. High voltage high resistance, and the capacitor is connected, and voltmeter is connected in parallel to the capacitor to measure the voltage across the capacitor. Now look at this derivation of capacitor charging. Consider the voltage law. We know that source voltage will be equal to the total voltage drop of the circuit. Therefore, voltage is equal to IR, that is instantaneous current in resistance, plus voltage V. V minus V, that is V minus V equal IR. Then from that I you can get it. I equal V minus V over R. Then we know that I equal to change in charge with respect to time. That is I equal to dq by dt. And from this Q, look at here, Q equal to CV, that is Q is charged. Then I equals dq, that is I equal, we know that dq by dt. Therefore here I equal to, by substituting Q equal CV, then we can write I equal to C equal into dV by dt, where C is outside the derivative, that is a constant. Therefore V minus V equal R C dV by dt. Therefore V minus V equal RC out of derivative and dV by dt. Now rearranging this equation, we get dt by RC. Look at here, from rearrangement, dt by RC is, that is reciprocal, equal dV by V minus V. Integrating, that is, look at here, integrating dt by 1 over RC is equal dV over V minus V. Here some, for simplification, let's some simplification here. Let U equal V minus V. This V equal U equal V minus V. Then du by dV equal minus 1, because here V is a constant. Small v minus 1. Then du equal, by cross multiplying, du equal to minus dv. Therefore, we are substitute these values here. Therefore, minus 1 over u du equal minus log u. Substitute u value, that is minus, that is integral of minus 1 over u equal to minus log u with respect to u. Then log u. Therefore, you can write minus log u equal to minus log v minus v. On integrating this, we get T over RC plus K equal minus log v minus v. Therefore, we can say minus T over RC plus K equal log of v minus v. As we are considering an uncharged capacitor, that is zero initial voltage, the value of K can be obtained by substituting the initial conditions of the time and voltage. At the instant of closing the switch, the initial condition, that is t equals 0 because time starts, and voltage across the capacitor V equals 0 because just now it stopped. Thus we get log V equal to K. That is here, putting 0 here, log V equal to K because here time equals 0, then K equal to log V. Then K value you are substituting here, that is minus T over RC plus log V equal log of V minus V. Therefore minus T over RC is equal log V minus V minus log V. Then we know that log M minus log N is log M by N, that is minus T over RC equal log of V minus V over V. Subtraction becomes division for the log. Taking exponential e power, we are taking exponential e power minus T over RC is equal to e power log of anything is only that. Therefore, it becomes V minus V over V. Therefore, this is our equation, that is e power minus T over RC equal to V minus V. By rearranging, that is by cross multiplying, that is V come here, that is V into e power minus T over RC equal to V minus V. From this we get V come this side, this go here, that is V equal V minus V into e power minus T over RC. From this we get, take off V common both sides, you will get V into 1 minus e power minus T over RC is the voltage equation when charging. Instantaneous voltage at any time. If you put the time here, we'll get the instantaneous voltage. This V is your full voltage supply. From this above expression, it is clear that the instantaneous voltage will be a result of the factors of such capacitor, capacitance, resistance in series with the capacitor, time and applied voltage value. Here, look at V max here. Here this is V max at 0.632 times V max is here. As the value of constant RC increases, the value of exponential function is e power minus T over RC also increases. This is a negative things here. It increases, that exponential function also will increase. That is, the rate of voltage rise across the capacitor will be lesser with respect to that time. That shows the charging time of a capacitor increases with the increase of the time. Charging voltage increases with the increase of the time constant RC. This time constant is RC here. Time constant RC. Then the value of T increases, the term e power minus T over RC reduces, and it means the voltage across the capacitor is nearly reaching its saturation value. Look at here, the expression for the voltage across the capacitor is derived as, look at here, V equal V into 1 minus e power minus T over RC. V is the source voltage, big word V, smaller v is instantaneous voltage, C is the capacitor, capacitance of the capacitor, R is the resistance connected in series, T equal to time. The voltage across the capacitor, we know that V equal to Q over C. Here Q is the maximum charge. The instantaneous voltage V equal to Q over C. From that Q equal to instantaneous charge. Therefore Q over C equal to, instead of V, we are writing Q over C here, e power 1 minus e power minus RTC. Then Q equal Q into 1 minus e power T over RC is the charge equation. Here time constant is RC and charge Q equal to maximum charge into 1 minus e power minus T over RC. Now charging current. Here for a capacitor, the flow of the charging current decreases gradually to zero in an exponential decay function with respect to time. We know that equation V equal instantaneous voltage V equal to V into 1 minus e power minus r minus t over c RC, then V equal to that V, open the bracket, V into e power minus RTC. Then from this, then V equal V minus V into e power minus t over RC, then V equal to V into e power minus t over RC. Now voltage we can find now. Therefore from here we can write V equal, look at here, then the source voltage capital V equal voltage drop across the resistance IR plus voltage across the capacitor V. Therefore, we can write V equal IR plus V, that is V minus V equal to IR. Substitute V minus V equal IR in the equation before here. Then you can get it. Therefore, IR equal to V into e power minus T over RC. Therefore, I equal to V over R minus e power minus T over RC. This instantaneous current equation. As V is the source voltage and R is the resistance, V by R will be the maximum value of current that can flow through the circuit. That is V by R equal to I max, then I equal to I max e power minus T over RC. That is I equal I into, that is I max e power minus T over RC. This is an instantaneous current equation through capacitor. Now we will discuss about discharging the capacitor. Suppose here the switch is closed as well as, that is, look at here, remove the battery and connect the terminals of the battery short circuited, then discharge starts. For discharging capacitor, the voltage across the capacitor V decreases to zero. That is why we remove the discharge capacitor voltage and terminal voltage and short circuited, that it becomes zero. Therefore, applying Kirchhoff's voltage law, V is equal to the voltage drop across the resistance R. Therefore, V instantaneous voltage plus IR equal to 0. From that, we know that I equal to dq by dt, that is C dV by dt. Yes, we are substituting Q values. Therefore, the current I through the resistor is rewritten as substituted equation 1. Therefore, V plus RC dV by dt equal to 0. Then V equal to minus RC dV by dt, come here, and dt by RC. dt by RC by reciprocal will get dV by V. We know that integration of dV over V. The integrating and rearranging the above equation will get 1 minus 1 over RC, take out of the integration, and dt is equal 1 over V dV. Now, constant, that is minus T over RC, is dt integration is T plus constant of integration K equal to 1 over V integral is log V. Therefore, log V equal then minus T over RC plus log V. That means the K value is log V. At initial conditions, from using initial conditions, we can get K values, that is here log V equal minus 2 over RC plus log V. Now collecting one side, that is log V minus log capital V is equal to minus Q over RC. Then log M by N is log V over V, which is equal minus T over RC. Applying exponential function, e power log of V by over V equal to V over E. Here e power minus Q over RC. From this, by cross multiplying, we will get V equal V into e power minus T over C, discharging equation for voltage. The instantaneous voltage across the discharging capacitor is V equal to V into e power minus T over RC. Instantaneous charge Q equal to Q into e power minus T over RC. Instantaneous current I equal to minus I max e power minus T over RC. This is the result. Look at your figure for discharging voltage. Here voltage axis, here current axis. Then instantaneous current equal here. For the above equation, it is clear that the voltage, current and charging of capacitor decay exponentially during the discharge. The discharge current has a negative sign because its direction is opposite to the charging current. So far we discussed about capacitor charging and discharging and time constant, exponential decay, some expression for charging and discharging of the capacitor we have done. Please subscribe our YouTube channel.